Here we are going to discuss about reflection and refraction of the wave, that the wave may not be travels in a particular medium always, that the wave may travel from one medium to another medium. The similar type of concept we observed in our boundary conditions, right? Similarly, the wave may travels from some free space to a dielectric medium, or one dielectric medium to another dielectric medium, or it may hit sometime a pure conducting medium. Like that we have different phenomena, different conditions. Now we are going to observe what is the equation of all those things, or so the wave for all those conditions. Whenever the wave is traveling from one medium to another medium, so how the characteristics will be varied and how the equations can be written. Now what we are going to observe here. Before that, just imagine a light ray. Same as our light ray, here also electromagnetic ray, electromagnetic wave, that what we can say, will travels from one medium to another medium with a little refraction. That already we observed in our boundary conditions, right? So whenever the wave is traveling from one medium to another medium, same as light ray, it takes refraction and it takes some reflection. So here clearly we are supposed to observe three different wave equations. So what is the actual ray or the actual wave which is traveling? That is nothing but the incident wave. And what is the wave which is transmitted? Is nothing but the refracted. And what is the ray or the wave which is reflected? So like that, three different equations we are supposed to observe. If you understand and if you imagine, it is not that much difficult. Just here we are observing a wave at the boundary of two different mediums. And in this particular case, we are observing a normal incidence. Normal incidence means a perpendicular incidence on the boundary what we are considering. The wave is traveling perpendicular to the boundary of two mediums. So exclusively put this case as normal incidence. Now imagine, so we have two mediums, that clearly there will be a boundary between those two mediums. As an initial case, I will consider these two mediums as two different dielectric mediums, a lossy dielectric mediums, that what I am assuming. So every dielectric medium will be characterized, or every medium will be characterized with the permittivity epsilon 1 for first medium, it is a mu 1, permeability mu 1, and sigma 1 is the conductivity of the first medium. In the same way, consider the medium 2 has epsilon 2, mu 2 and sigma 2 as its parameters. Now whenever the wave is traveling from medium 1 to medium 2, how the equations can be written and what is the direction of the particular electric field or magnetic field, and what are the equations of magnetic field? This is the thing that what we require. So initially what I do is, I will try to give you, so one by one, what is the equation of incident wave. So and what is the direction of that particular wave. So as a general case, once again take that the direction of wave propagation is z. A universal notation that what I am considering, the direction of wave propagation is z. So and assume that this boundary is at z is equals to 0. Clearly the boundary is at z is equals to 0. If it is at z is equals to 0, I am assuming that the wave propagation is positive z direction. So let us take this is a positive z direction. Let us take the opposite one is a negative z direction. In the medium 1, the wave is there, the incident wave is there. The incident wave is traveling in which direction? Positive z direction. So clearly take this is the direction of wave propagation. That is, it is traveling in positive z direction. Since it is traveling in positive z direction and it is a uniform plane wave, it may contains the electric field and magnetic field perpendicular to the direction of wave propagation. And I am assuming that the electric field is along x direction, the magnetic field is along y direction, right? So let us take initially the electric field along x direction is like this. So take this one as E. Since it is incident, I am writing this one as EI. The notation I stands for incident wave, and clearly it is perpendicular to the direction of wave propagation, right? And it is on x direction, along x direction, and perpendicular to this one. Clearly what I am doing is I am assuming that the H field is away from the plane of paper or the plane of board here. Since it is away from the plane of board, I can represent that one with the tip of arrow like this and name it as HI. Clearly observe what I am doing here. Initially I am considering the direction of wave propagation is z. Since the direction of wave propagation is z and it is a uniform plane wave, I can consider the electric field perpendicular to that one, and I am assuming that that is in x direction, and the h is away from the board, that's like this, it is incident h, right. Now it is traveling in medium 1. Initially that is the wave that what we have. If it is traveling in medium 1 and when it hits the boundary, what happens to it? Just imagine, this is the signal that what we have, electric field is this one, magnetic field is this one, it is traveling towards me, it is traveling just like this. Whenever it hits the boundary, what happens to that? You need to imagine here, right. This is the electric field, this is the magnetic field, and it is traveling like this. This is the boundary, it is traveling like this and hits the boundary. Whenever it hits the boundary, it takes a reflection like this. Clearly observe. So it hits the boundary and it takes a reflection like this. So whenever it is taking a reflection, the direction of the thumb, that is nothing but the electric field, unaltered. The electric field is in the same direction, but the direction of magnetic field was altered. Initially this is the direction of magnetic field, but after reflection the direction of magnetic field was altered and the direction of wave propagation also changed. Initially this is the direction of wave propagation, after reflection this is the direction of wave propagation, right. So with this is the assumption what you have to do, and this is the imagination what we have to take, right. So clearly the wave is traveling like this up to the boundary. Whenever it hits the boundary, it is taking reflection. Whenever it is taking a reflection, it is traveling in opposite direction. Opposite direction means negative z direction, right. And the direction of electric field is unaltered, but the direction of magnetic field is altered. Magnetic field was changed. Now clearly I am writing the reflected wave here, just you understand what I am taking. This is the direction of reflected wave, right. What is the direction of this reflected wave? Negative z direction. And what is the direction of electric field? The direction of electric field is same as the previous one, right. Here I am writing the electric field direction which is reflected as ER. The electric field direction which is reflected is same as incident ER, but direction of magnetic field is, now it is into the plane of paper or into the plane of board. In the previous case it is out of the plane of board and now it was altered the direction. Now you have to represent that one into the plane of board, that's why I am writing it is just HR. Clearly observe. If you observe this figure, then the writing equation is very simple. So initially this is the traveling wave, so traveling in positive z direction, it hits the boundary and it is taking a reflection. In the reflection, the direction of wave propagation was changed to negative z. The direction of electric field intensity is same as our previous one, but the direction of magnetic field intensity is now into the plane of board. That is regarding the reflected wave. Then what about regarding the transmitted wave? Just you observe the transmitted wave. So the transmitted wave is same as our incident wave. It is not taking any difference in the propagation direction, and the direction of electric field is not altered. The direction of magnetic field is also not altered. So clearly you have to represent the wave as it is, as same as our instant wave, so within the second medium also. That's why just this is direction of wave when it is transmitted to the second medium. This is the same as our previous one, this is the direction of the wave, and the electric field also in the same direction, that is this is ET, that what I am writing. ET is nothing but the transmitted electric wave. So this is nothing but electric field same as our EI, and the magnetic field also will be in the same direction, that is it is out of the plane of paper or plane of board, simply it is HT. If you understand these three figures, then writing equation is very easy. That simply observe here, EI incident electric field, HI incident magnetic field hits the boundary. Whenever they hits the boundary, they returns or reflects. Whenever they reflects, the direction of wave propagation changes here, right. The direction of electric field same as previous one. The direction of magnetic field will be altered. Here the direction of electric field will be same as incident wave. The wave propagation direction is same as incident wave. The magnetic field direction is same as incident wave. So one by one we have to write down the equations for incident wave, transmitted wave and reflected wave. So what I do is, I will assume what is the equation of our incident wave initially. So let us take here in this space, in this particular space, I will try to write down the equations for all by observing these figures. So what I do is, in this particular space, I will try to write down the equations for all. So initially I am writing the equations for incident signal. So let us take EI is equals to some EI naught. EI naught is the initial electric field that what we have at 0 time or 0 space. EI naught e power minus gamma z. That clearly observe here that it is traveling in positive z direction, and initially what I am assuming is it is in x direction, right? That's why I will add a unit vector ax. So this is the initial equation of incident electric field. If electric field is known to us, the magnetic field can be easily written in terms of its characteristic impedance. Before that, what I do is, I will try to write down gamma 1 here. It is not gamma, just since we have a different medium, so gamma 1 can be obtained here and gamma 1 can be written here. So clearly E is equals to EI naught e power minus gamma 1 z ax is the equation for incident electric field. Then what is the magnetic field? Incident magnetic field is equals to, how we can write the relation between E and H? So simply it is EI by eta 1, where eta 1 is the characteristic impedance of the medium 1, right? So this can be written as EI naught divided by eta 1 e power minus gamma 1 z, and we are assuming that the incident magnetic field is in the direction of AY, right? So this can be written as just HI naught e power minus gamma 1 z AY. Just understand what I am doing here. I am taking the incident electric field in the direction of x and it is propagating in positive z direction. Magnetic field in the direction of y, it is propagating in positive z direction, and I am relating electric field and magnetic field with the help of intrinsic impedance or the characteristic impedance of the medium 1. Therefore HI can be written as EI naught by eta 1 e power minus gamma 1 z AY, right? Keep them aside, right? Now we are going to write down the equation for reflected wave. So if you are supposed to write down the equation for reflected wave, once again observe what are characteristics. For that, what I am doing is just I am writing the equation of electric field initially. Let us take ER, which is equals to some initial amplitude ER naught into, now what is the direction of this electric field? The propagation direction of this electric field, negative z direction, and it is in which medium? Same medium 1, right? So clearly we can write this one as e power minus gamma 1 and the direction is negative z direction. Clearly observe the difference here. It is in positive z direction, it is in negative z direction. And what is the direction of this electric field? X direction. Therefore I will write this one as AX. Writing the equation is very, very important, right? The reflected wave is equals to initial value some amplitude multiplied with the propagation constant gamma 1, since it is in same medium gamma 1, and it is traveling in negative z direction and the field exists in x direction only. So now we are supposed to write down the equation of HR also. For that, let us take HR is equals to some HR naught. HR naught is the initial magnitude of our magnetic field multiplied with e power minus gamma 1 multiplied with minus z, since it is traveling in negative z direction. I am adding minus z over there, right? Now what is the direction of this H? Initially it is in the direction of y, that's why you have added AY here. But here in the reflected case it is in the direction of negative y. The direction of this HR was altered. That's why the direction is minus AY. That this is the thing that what we are supposed to write down, right? Now instead of this HR naught, what you can write? ER naught by eta 1, right? So this ER naught by eta 1 I am writing instead of this HR naught, which is simply ER. So ER is nothing but ER naught divided by eta 1 e power gamma 1 z minus AY. Just directly as I am replacing this one. So this is the equation of our reflected magnetic field. So we got, as initially we assumed the incident electric field and incident magnetic field. Later from those two, reflected electric field and reflected magnetic field were obtained. these two are clearly traveling in negative z direction, and the direction of E was unaltered, same as this one, but the direction of H was altered. In the previous case it is ay, now in this case it is negative ay, because it is in altered direction, it is in negative y direction. Now we have to write down the equation for transmitted wave, right? The transmitted wave has same equation as our incident wave, but observe this transmitted wave is in medium 2, right? That is why what I am doing is I am writing the same equations again, but the medium characteristics like eta 1 and gamma 1 will vary. For that, clearly observe what I am doing here. The transmitted electric wave Et is equals to, I am taking the initial value as Et naught e power minus gamma 2z. That clearly it is in medium 2, that is why I am taking gamma 2z. Z means it is a positive, it is traveling in positive z direction, and the component of E is in x direction. That clearly Et naught is the initial value, it is traveling in positive z direction and it is in x direction only, right? In the same way, Ht is equals to, the transmitted magnetic field is equals to Et by eta 2. That what we have to write as Et naught divided by eta 2 e power minus gamma 2z, and it is in the direction of y. So clearly these two are the equations that what we can write for transmitted signal. So these are for incident waves, these are for reflected wave, and these are for transmitted wave. Now here we are supposed to get the relation between all these things. So with the help of a boundary condition that already we learned, we can get a very good and beautiful relation between these two terms, and from that we can define a very interesting terms like reflection coefficient and transmission coefficient. Now all these equations were compiled here. This is the incident wave equation, reflected wave equation, and transmitted wave equation. Now here we are supposed to observe the boundary conditions at the boundary of two mediums. Just recollect the boundary conditions. At the boundary of two mediums, the tangential component of electric field and magnetic field are continuous, that the tangential components are same. The normal component of electric flux density and magnetic flux density are continuous, right? So here what we are doing is electric field components, they are not flux, as electric field components must be continuous even they are tangential. Just observe, this is the boundary that what we have. Since it is a plane wave, for the direction of wave propagation, the electric field and magnetic field are perpendicular, right? Now if these two are perpendicular to the direction of wave propagation, they are parallel to the boundary, right? They are parallel to the boundary means they are tangential to the boundary. Clearly at the boundary what we have is tangential component of electric field, tangential component of magnetic field when it is traveling towards the boundary, right? That is the incident wave has tangential E and tangential H. Now when it is reflected, then also it is the tangential component. The E is tangential component, H is also tangential component. When it is transmitted, E is tangential, H is also tangential. So clearly identify and just observe that simple point. At the boundary from medium 1 or in medium 1, all the components what we have are tangential. In medium 2, all the components what we have are tangential. And in medium 1 what we have? The electric field which is incident, the electric field which is reflected, the magnetic field which is incident, and the magnetic field which is reflected. So in medium 1 we are supposed to observe the combination of these two. So exactly at the boundary, the electric field is a combination of incident and reflected. In the same way, in medium 2, exactly at the boundary we have only transmitted wave. Just remember this simple point and try to apply the boundary condition here. Since the tangential components are same, for our understanding I am writing the notation here. In medium 1, the tangential components are EIT, so the incident wave tangential component plus the reflected wave tangential component ERT, right? This is the total tangential component what we have in medium 1, which must be equals to, as per our boundary condition, the tangential component in medium 2, which is ETT. ETT is nothing but the tangential component for the transmitted wave. So this is for electric field. The similar type of condition can be applied for magnetic field also, right? That is HIT plus HRT is equals to HTT. That is the tangential component of incident wave plus the tangential component of the reflected wave is equals to, at the boundary, the tangential component of the transmitted wave. Now how to obtain the field components at the boundary? Just by simply substituting z is equals to 0. Since we are considering the boundary exactly at z is equals to 0, by substituting z is equals to 0, we can get all the tangential components. So what I do is just I will write down the equations one by one here, that EIT plus ERT is nothing but EI of 0 plus ER of 0, which is equals to ET of 0. Similarly, it is HI of 0 at the boundary plus HR of 0, which is equals to HT of 0. But here, instead of HI of 0, HR of 0 and HT of 0, we can write down the equivalents in terms of electric fields, or the similar equations can be written as, just what I am doing is I will consider, so directly instead of this EI naught, we can write down the initial value EI naught. EI of 0 can be written as EI naught plus ER of 0 can be written as ER naught, which is equals to ET naught. That's what I can write. Right? In the same way, HI of 0 can be written as HI naught. So which is simply HI naught plus HR of 0 can be written as HR naught, which is equals to HT of 0 is nothing but HT naught. That's the initial value HT naught. Right? But what I am doing is I am rewriting this HI naught, HR naught and HT naught in terms of electric fields and the characteristic impedances. So this HI naught can be equated to HI naught is equals to EI naught by eta 1. So this HI naught can be written as simply EI naught by eta 1. HR naught can be written as HR naught is equals to minus ER naught by eta 1. So minus ER naught by eta 1, which is equals to HT naught. HT naught is can be written as simply ET naught by eta 2. So which is equals to ET naught by eta 2. Just observe. So what we are doing is at the boundary we are applying the boundary conditions. The tangential components of electric field are continuous. The tangential component of the magnetic field are continuous. Since at the boundary we are applying z is equals to 0, that we are taking the initial values here. That EI naught plus ER naught is equals to ET naught. This is the equation what we are supposed to take for simplification. Later, the tangential component of magnetic field was written in terms of electric field. That EI naught by eta 1 minus ER naught by eta 1 is equals to ET naught by eta 2. That EI naught plus ER naught we have, EI naught minus ER naught we have, and on the right hand side we have ET naught. These are two simple mathematical equations. If we solve those two equations, we will get two conditions. That in terms of ER naught and EI naught, and in terms of ET naught and EI naught, we will get two equations. Directly I am writing those two equations. That the equation will be like this: ER naught is equals to eta 2 minus eta 1 divided by eta 2 plus eta 1 multiplied with EI naught. Just once again I am saying, simplification of these two equations by eliminating ET naught, we will get this equation. Now here what we have, ER naught, that is the reflected electric field, EI naught, incident electric field we have. If you take the ratio of these two, that is ER naught divided by EI naught, which is equals to eta 2 minus eta 1 divided by eta 2 plus eta 1. This is called as reflection coefficient. That clearly how much amount of electric field is reflecting when some amount of incident electric field is incident. Simply this is said to be the reflection coefficient and denoted with a symbol capital gamma, and this is a dimensionless one, and clearly this may be a complex one also. Since eta 2 and eta 1 are complex, this is also may be complex, right? So this is called as the reflection coefficient. This describes how much amount of energy or the electric field was reflected when it hits the boundary. In the similar way, if we solve the equations and eliminate this ER naught, we will get one more equation. That the equation will be like this: ET naught is equals to 2 eta 2 divided by eta 1 plus eta 2 multiplied with EI naught, and after rearranging this one, we will get one more relation, that is ET naught divided by EI naught, which is equals to 2 eta 2 divided by eta 1 plus eta 2. So this is one more important relation we are supposed to remember. And here clearly observe what we are doing, it is relating the transmitted electric field with incident electric field. That the ratio of transmitted to the incident is called as transmission coefficient, denoted with T. So here clearly we have two coefficients, that the transmission coefficient, how much amount of the electric field was transmitted to the second medium, and how much electric field was reflected within the first medium. This is called as the reflection coefficient, and this is called as a transmission coefficient. That we have a simple relation between these two. The reflection coefficient and transmission coefficient can be related as the transmission coefficient is equals to 1 plus gamma, that how much amount was transmitted is equals to 1 plus our reflection coefficient. And clearly just remember these two parameters are the two quantities, that these two are dimensionless and these two may be either complex one or real one, that is purely depend upon the conditions, right. And here what will be the limit for this gamma? Always the gamma lies between 0 and 1. Clearly remember that limit, that 0 less than or equals to the magnitude of gamma less than or equals to 1. If we are saying that gamma is equals to 0, reflection coefficient is equals to 0, corresponds to there is no reflection, that the entire wave was transmitted, then you will get tau is equals to 1. If it is equals to 1, if the reflection coefficient is equals to 1, the entire wave was reflected, that may be minus 1 or plus 1, since we have a mod term here, this may be minus 1 or plus 1, that purely depend upon that one, this tau will vary. So if tau gamma is equals to 1, entire wave was reflected. If gamma is equals to 0, entire wave was transmitted. That's what we are supposed to observe. Now what we do is just we will consider a special case when this will be transmitted and when this will be reflected, by considering two different mediums. In our previous case what we took is just a lossless dielectric medium as a general one. Now let us take the second medium is a pure conductor. If the second medium is a pure conductor, what about these values we will examine. Now let us take a special case. In that one what I am doing is I am taking the medium 1 as a lossless dielectric medium and medium 2 as a perfect conductor medium. So for that, for a lossless dielectric medium, let us take this is medium 1 and this is medium 2. Since the medium 1 is a lossless dielectric medium, sigma is equals to 0 and we may have some epsilon and mu, and the second medium is a perfect conductor. Since it is a perfect conductor, sigma is approximately equals to infinite. It's a very very high value and it may have some epsilon and mu, right. Now we are supposed to observe what is the reflection coefficient at the boundary. So for the calculation of reflection coefficient, take gamma is equals to eta 2 minus eta 1 divided by eta 2 plus eta 1. Calculate the characteristic impedance of the second medium. So what is the basic equation for characteristic impedance of the second medium? Eta 2 is equals to, just you go for the basic equation. If you are unable to remember, go for the basic equation, which is equals to j omega mu by sigma plus j omega epsilon, which is equals to, since sigma is very very high value, in the denominator what we have is a very very high value, approximately this eta 2 must be equals to or maybe equals to 0, right. And what about this eta 1? Since sigma is equals to 0, j omega mu by j omega epsilon, omega j omega will be cancelled, that epsilon eta 1 is equals to just under root mu by epsilon. So here the eta 1 is existing, that here eta 1 we have, but here eta 2 is equals to 0, right. Now substitute here, which is equals to eta 2 is 0 minus eta 1 divided by 0 plus eta 1, which is equals to minus 1. So what is the meaning of gamma is equals to minus 1? As I said, if gamma is equals to 1 or minus 1, the entire wave will be reflected. That what we are expecting at the boundary of any conductor. So clearly within the conductor there will be no wave propagation. The wave will be completely reflected from the boundary of any conducting medium or perfect conducting medium, that what we can say. But here whenever it is reflecting, it is taking 180 degrees phase difference or phase shift. That what we are supposed to observe with the help of this negative one. So with the definition of this gamma, how we can write this one, that ER naught divided by EI naught is equals to minus 1, which corresponds to ER naught is equals to minus EI naught. So whenever we have a conducting medium as the boundary, immediately the reflected wave is equals to the incident wave. And what about the transmission coefficient? The transmission coefficient T is equals to 1 plus magnitude of gamma. That's a 1 plus the magnitude of gamma is minus 1. That is 1 minus 1, which is equals to 0. Since the entire ray is reflected, definitely there will be no transmission. So clearly remember this particular point. Whenever the wave is traveling from a perfect dielectric medium to the perfect conducting medium, exactly at the boundary, it takes a reflection with same amplitude. So you have to imagine a simple scenario. The wave is traveling like this, it hits the boundary, and with same amplitude it is traveling in opposite direction. Then what happens? Here a wave which is not propagating in space will be occurred. That is called as a standing wave. Here it has no direction of wave propagation, just it stands in that particular medium. That is called as a standing wave. That here to understand this one clearly, you need to imagine a simple scenario. Let us take two water pipes. So those two water pipes are dispensing same amount of water with the same force. That they are traveling with same velocity and same amplitude they have. Right, same amount of water with the same force. If they hits at a particular point, that is one is incident wave, another one is the reflected wave, the water will not move in either direction. This water will not move to this direction, this water will not move to opposite direction, just they will stay there. The same way, the incident wave and the reflected wave both have same magnitude and it's opposite in phase and they are traveling with same velocity. Then the wave which occurs as a resultant of these two is called as standing wave. This standing wave phenomena is very important in some of the communication systems. This will occur whenever there is a reflection. And how this standing wave ratio was defined? Clearly this standing wave ratio was defined as the ratio of maximum to the minimum electric field or the maximum to the minimum magnetic field, and it is denoted with a simple symbol S. So that's what I am giving here. So the standing wave ratio S is equals to, it is the ratio of electric field maximum to the electric field minimum or magnetic field maximum to the magnetic field minimum. And simply we have a relation between the reflection coefficient and that standing wave ratio, that these two can be related as 1 plus magnitude of gamma divided by 1 minus of magnitude of gamma. And what is the upper and lower limits of this S? Since gamma is varying from 0 to 1, the lower value of this S may be 1 and upper value is infinite. So clearly identify that gamma is varies from 0 to 1 and the standing wave ratio is always varies from 1 to infinity. Maximum standing wave ratio, that what we have is the maximum reflection. So clearly remember these simple basics which are related to the wave reflection. Here the most important parameter is that identifying the parameters are the equations which are associated with our electric field when it is taking incident and when it is taking a reflection from the boundary and when it is transmitting to a particular medium, and how the characteristics will be varied. So here in this particular case I am considering a conducting medium and dielectric medium, and this may not be always like this, and as per the requirement we are supposed to take different mediums, and according to that one we are supposed to observe reflection coefficient, transmission coefficient and standing wave ratio. And clearly remember that this standing wave ratio will occur whenever there is a reflected wave. If there is no reflected wave, the standing wave will be 0, that there will be no standing wave, but the ratio may be 1, that the ratio is equals to 1 means there is minimum standing wave, that what we can say. So with this one the reflection, refraction and the transmission of a normal incident wave can be completed. So with these basics we can solve a few problems which are related to our wave propagations in our next session.